All right, so let's go ahead and get started. So just for those of you who registered to class recently and maybe didn't get the original invitation to join Top Hat, I will be sending out a new invitation today just for the people who haven't already received it, okay? So your first homework assignment will be released on Thursday, will be released on the 19th, right? And so I will briefly go over it in class just to make sure that everybody's sort of on the same page in terms of its format and whatnot. So for the next couple of days, we're going to be talking about meteorological measurements and basically how we display these things. So how do we make these measurements? We know that we have sort of measurements of temperature, pressure, wind, and moisture. So we're going to talk a little bit today about how we make those measurements and probably a bit more next class about how we actually display them. And when we talk about the mechanisms or the sort of tools that we use, these are just some of them, right? So surface measurements are probably things that just about everybody's familiar with. When you get your report of what the temperature is doing at Montreal, that is a surface measurement, right? That next thing that looks kind of complicated, rayons, those are actually weather balloons, right? So when you hear people talking about weather balloons, and we'll go over all of these things individually, those are measurements that we take throughout the depth of the atmosphere. And we don't take them everywhere, but we do take them around the world. We'll talk about radar, and then we'll talk a little bit about wind profiling, but we're not going to spend too much time on this because this is sort of a minor thing. But we will talk about satellites, satellite pictures and satellite imagery, and we'll talk a little bit about lightning detection. We can actually tell when lightning strikes the Earth based on the magnetic field or the electromagnetic field that the lightning bolt creates. So we can actually tell where that's happening and how strong that lightning is. So we'll discuss again the analysis of measurements today, and then we'll discuss how we actually turn that into a weather forecast in a future class. Now, one of the things that we have to do when we go ahead and make measurements is that we have to make sure that our measurements are coordinated, right? So basically everybody has to be taking measurements at the same time around the world. Okay, so when we do this, when we take measurements globally at the same time, these are called synoptic measurements. And the term synoptic simply comes from the Greek synopsis, right? So it's a summary of what's going on. And actually, the field of synoptic meteorology is actually what I specialize in. And again, that's sort of the synthesis of what's going on, either regionally or globally. Now, since we have to coordinate our times across the globe, we actually use something called Coordinated Universal Time, or Greenwich Mean Time. So when we talk about meteorological timestamps, we're essentially using the time in Greenwich, England. Okay, so on the 0 degree meridian is basically what our standard time is. So when you look at a weather map, what you'll actually see, for instance, you might see something like a measurement at 12 UTC, which is basically noon in Greenwich, England. Okay, and that would correspond right now to 7 a.m. our time, right? So noon in Greenwich would be 7 a.m. Eastern, right? And that's because we're in standard time. Once we move the clock, that changes. So this table just shows you the corresponding timestamps, right? So basically it just shows you this is midnight, Greenwich Mean Time. This is noon, Greenwich Mean Time, and what that corresponds to in terms of the different time zones across North America. So there's nothing really complicated about this. It's just like you having to know if you want to call your friend in England, you have to know what the time difference between us and them are. All right, so it's the same idea. You simply have to know what the time difference between Greenwich and whatever the time zone you're in is. So for instance, we can have something that looks like this. And this is a surface map from January 13th of 2015. And this is 21 UTC, which is the same as 4 p.m. local time. Okay? And so what this is just showing is that these are the observations, and we'll talk more about this a little bit later. These are the observations across North America, well, at least a portion of North America. And what this is actually showing you is temperature, dew point, wind, and we'll actually talk about how to read this map in a little bit. Now, unfortunately, a lot of the maps that are sort of consumer friendly or at least readily available on the internet are from the United States, which means that they're in Fahrenheit and not in Celsius. And so the United States is a little schizophrenic. All of its surface maps will be in Fahrenheit, and all of its maps representing things that are happening in other levels in the atmosphere are in Celsius. And the types of observations that you just saw are taken essentially by an instrument array that looks something like this. Okay, and there's actually a lot of information being recorded, a lot more than you're actually seeing on a map like this. This is a very distilled version of what's going on, even though just on this map, it's giving you wind direction, it's giving you how much cloud cover there is, it's giving you whether there's rain or snow or anything like that, temperature, dew point, pressure, all of that is encoded on this map. But our instrument arrays also have things like they have freezing rain sensors, they have sensors to tell you how high the bottom of the clouds are, so you can tell where the ceilings are. This is really important, right, for aviation. For planes, they need to know like where the cloud decks are and where they aren't. There's rain sensors. There's also rain gauges, so there's going to be a tipping bucket, usually somewhere where they actually measure how much rain is falling. There's a visibility sensor, so that's telling you how far you can see, or measuring how far you can see. And so these are all things that are recorded. And again, the purpose of this originally was for aviation. And obviously this is still a huge reason that this happens. But generally speaking, the two main purposes of this are aviation and weather forecasting. Now, the coverage of stations is not uniform. All right, basically, if you look at a map like this and you look at the coverage of weather stations, you'll basically notice that there are more stations where there are more people. All right, so around cities, et cetera, we tend to have better coverage. So for instance, along the Northeast corridor of the United States, around some of the major cities in the Midwest, along the immediate West Coast, but once you get into the mountains, it gets a little more sparse. And then obviously as we get up further north into south into more remote locations, the number of surface stations that we have is highly variable. And so if you want to become a forecaster, I can assure you that trying to forecast for regions up here is considerably more problematic than trying to forecast for regions, say, in southern Canada or the United States. The amount of information that you have is not the same. All right, we have more information in southern Canada and in the United States than we do in northern Canada. And so the quality of our weather information is not anywhere near as good. And this can have an impact. So basically I have a map similar to the one that I showed you earlier. And I have a couple of stations sort of blocked out. And again, these temperatures are in Fahrenheit. So there's a temperature of 14 degrees Fahrenheit there, a temperature of 16 degrees Fahrenheit here. Now, all things being equal, if you did not have information where those blue boxes are, and you tried to guess, or you tried to interpolate what the temperature at those blue boxes were, you might guess something like 15 degrees. All right, it's just in between the 14 and the 16. Problem is if you did that, you would be pretty wrong, because the temperature is actually closer to 27 degrees C. Okay, so whenever you have valleys, mountains, things like that, the coverage of surface stations becomes really important. And there are times, Burlington, Vermont is situated right about here. Now, there are times where the difference in temperature between Burlington and Montreal is actually just south of that 14 degree, just southwest of that 14 degree thing that I circled earlier. There are times where the temperature difference between here and Burlington can be upwards of 10 or 15 degrees C. Okay, so you have to be highly cognizant of what's going on. And that is largely controlled by the fact that we have valleys running in different directions, and as well as we're surrounded by mountains on basically all sides. Okay? So the coverage of surface stations is actually pretty important. And this is what we call a station model, or essentially how to read the weather maps. Okay? Now, we're going to start with the wind here. Okay, so remember the wind barbs that we talked about. This is the same convention. So the circle is the head of the arrow. The barb is the tail of the arrow. So this wind is blowing from southeast to northwest, right? Okay, so this would be compass heading, that would be north, and this would be east, right? So the wind is actually blowing from southeast to northwest. It's blowing at 10 knots. Okay, so that's giving you the wind direction and speed. What's going on in the circle is basically telling you what the sky cover is doing. So a half-filled circle is essentially partly cloudy skies. And you can actually see the cloud cover insignia down here. Okay, so obviously the cloudier it is, the more filled the circle becomes, until the point where you cannot actually see the sky. Usually that's due to precipitation. If it's raining heavily or snowing heavily, you won't actually be able to see the bottom of the clouds. And at that point, you'll see an X, which means that the sky is obscured. The top number here is the temperature. The bottom number here is the dew point. Let me erase this for a sec. And then there's one other thing. Oops. That is the pressure. But it's obviously not the full pressure. We said that the pressure near the surface is generally speaking around 1,000 hectopascals. All right, so we said that the mean sea level pressure, the standard pressure, is about 1,013 hectopascals or millibars. So the way this pressure is encoded, it's in tenths of a millibar or tenths of a hectopascal. So you would read this as 0.4.2, okay? And now there's an implied 9 or 10 ahead of it. So this pressure is either 904.2 hectopascals or it's 1,004.2 hectopascals. The one that it is the one that is closer to 1,000 hectopascals. Okay? So since you see a 0.42 here, your pressure is actually 1,004.2 hectopascals in this case. If the number you saw there was 721 or 721, then your pressure would be 972.1 hectopascals, because 972 hectopascals is closer to 1,000 than 1,072 hectopascals is. So you have to infer the 9 or the 10 that goes in front of that number. And the way to do that is to simply use the choice that gives you a surface pressure closest to 1,000 hectopascals. But this will always be in tenths of a hectopascal. So this can be, this could actually read 000, which would mean that it is 1,000.0 hectopascals. All right, and it could read 121, and that would be 1,012.1 hectopascals. So really large numbers would tend to have a 9 in front of them. Really small numbers would tend to have a 10 in front of them. And then the symbol in between the temperature and the dew point is what is actually falling from the sky, if there's any precipitation. Now, I don't expect you to memorize all of these symbols per se, but I do expect you to know the difference between rain and snow, and the difference between light snow and heavy snow, and light rain and heavy rain, right? So the number of dots indicates the intensity. So the more dots, the higher the intensity. And then whether you have a dot or an asterisk will basically dictate whether it's rain or snow. There was a question over here. So, I mean, your dividing line would be something around 50 or 500, right? And so actually, if this number read 500, it would be somewhat ambiguous if the actual pressure is 950 hectopascals or 1,050 hectopascals, because both of those are essentially equally likely. And so at that point, you would need more information to know. But generally speaking, those types of situations are rare, right? Usually we won't see pressures either at 950 or 1050. But yeah, so literally at the halfway point between the two is about the break-even point. Yeah, so when we talked about winds last class, we basically said that it was the barbs at the back were telling you the strength. So a full-length barb is 10 knots. If there were 2 barbs, it would be 20 knots. If there was 3, et cetera, it'd be 30. And a half barb is 5 knots. So if there's a full barb and a half barb, that's 15. Okay, are there any other questions on how to read this? Yeah? Mm-hmm. So the wind would be blowing. The way to think of this is to just think of this circle as the head of an arrow, right? So the wind is actually blowing literally, if my hand is pointing in the same direction, so the wind is literally blowing in this direction on the map. Okay, so, and the map will always be sort of north-centric, right? So it would be always north would be upwards, east would be to the right. And so this, in this case, the wind would be blowing from this direction up in this. So, I don't know, does that answer your question? Yeah. Yeah, so just always think of the circle as the head of the arrow and the barb as the tail. And that will give you the representation in sort of vector form. And so where that circle is just a representation of where the station is. So the circle is actually, so if this were an observation from Montreal, the circle would simply be where Montreal is. I don't know if you noticed this, but actually they don't have it on this one. But all of these are essentially airport and airport codes. So Montreal would be CYUL. Now, one of the things that we kind of have to do that's a bit important is when we're measuring pressure, we have to account for the fact that if we go up a mountain, the pressure is actually going to decrease. All right, so we actually have to adjust for this fact. So for instance, if we decided to just map the pressure at every station across North America, the map that we would retrieve would look like a map of terrain, right? Because if we actually took the pressure by Calgary, the pressure would be something like 800 hectopascals, because Calgary is well above sea level. Pressures near Montreal would be about 1,000. And we're basically comparing pressures at 2 different elevations, which is not what we want, right? So when we want to compare pressures, we need to compare pressures at the same elevation at every point. So when we run into a situation where we have a mountain and the pressure is lower because we're higher up, we actually have to correct that pressure. And we correct that pressure by doing something that we call reducing it to sea level. So we essentially estimate what the pressure would be if the station was actually at the same elevation as sea level. And that's an estimation, right? We have to make certain assumptions in order to do that. So the pressure is actually fictitious. It's not real. It's something that we made up, but it's a representation of what the pressure should be at around sea level. Now, we also take measurements over the oceans and buoys, right? And so when we have a buoy, not only are we taking measurements of temperature and pressure and dew point, we're also taking measurements of waves, wave speed, currents, wave heights, and ocean temperature as well. Okay, so we also have a series of ocean buoys. Now, the primary weather tool that we have is, or observation weather tool that we have, is a weather balloon. Okay, and so weather balloons are launched twice a day around the world, and they're launched at noon and midnight Greenwich Mean Time. So for us currently, that would mean that the balloons are launched at 7 a.m. and 7 p.m. local time. Okay? And it is literally a little packet. It's literally about this big. And in this little packet, we have temperature and pressure and moisture sensors. And we simply attach it to a balloon and we let it go. And obviously, the balloon has to have a certain rate of rise. And the way we actually tell the wind from this is by tracking the movement of the balloon. There's a little GPS in the instrument package. And so by tracking the change in the position of the balloon, we can actually tell which way the wind is blowing and how strong it is. And so the wind is inferred from the change in location of the weather balloon. And then all of the other things are measured from the instruments themselves. And so we actually launch, this is actually launched not from Montreal per se, but it's launched from a location about 100 kilometers, 150 kilometers northwest of here, Maniwaki. And I don't know if you can't actually see it, but there's this little address label here. Eventually the balloons burst. The instrument packages fall back down to the ground. If you find one, you can drop it in a mailbox and it'll be sent back to the government for reuse. This is the location of the weather balloon launches across North America. And so you can see that there's a lot fewer of them than there are surface stations. All right, so we don't launch as many weather balloons as we have surface stations, but we have a pretty periodic coverage across most of North America. Now, obviously, the oceans are an issue, right? We're not launching weather balloons out over the ocean, generally speaking. Obviously, we have a few, it's like places like Hawaii and some of the Caribbean islands, but ocean coverage is definitely an issue. And they're actually fairly cheap, relatively speaking, right? So they only cost about $150 per instrument. And yeah, so if you do some simple calculations, the number of stations across North America, it runs out to about $8 million per year. And so on the grand scheme of things, that's really not that much money in terms of, you compare it to the price of a satellite, which is several $billion. All right. Of course, a satellite can last for order of years, but again, This is not that expensive a thing. And so what we do when we launch these balloons is it gives us a trace of temperature and dew point with respect to pressure or height. So what is this graph that I'm showing you? So on the bottom axis here, we have temperature, right? So we have cold temperatures on the left-hand side, warm temperatures on the right-hand side. These temperatures are in Celsius. And then there are two lines here. There's a temperature line and a dew point line. Now remember that the temperature has to be equal to or greater than the dew point at all times, right? So the temperature line will always be the line that's on the warmer side of the graph. So the temperature line, in this case, is the line will always be the line to the right. And you'll notice that at some points, the temperature line and the dew point line are the same. That tells you that in that layer, the relative humidity is 100%, which likely means that there are clouds. So if I was looking at this sounding, I would actually say that, well, I expect clouds to be present essentially from here to here, right? Because that entire layer indicates a relative humidity of approximately 100%. And so what we're actually seeing is the temperature changing with respect to height. So height is increasing this way, and pressure is decreasing. So what you're actually seeing on the left-hand side is a measure of pressure, 1,000 hectopascals, 900 hectopascals, 800 hectopascals. And you'll notice that the distance between those surfaces actually becomes larger and larger as we go up. That is because the atmosphere is getting thinner and thinner as we go up. So the distance between pressure surfaces actually increases as we go up. Okay? And approximately, when we talk about height, you can correlate that to height roughly using this scale. Okay, so for instance, we could say that we would expect from this sounding, we would expect clouds to exist from about 3.5 kilometers to about 10 kilometers, roughly speaking. And then on the side here is the winds in the different levels of the atmosphere. All right, so at 600 hectopascals, the winds are essentially blowing from the southwest or the west-southwest at about 25 knots, according to this. That would be 600 hectopascals. That's here. That would, that actually, sorry, corresponds to about that. So that's southwest at about 50 knots. West-southwest at about 50 knots. Okay, so this is basically giving you a snapshot of what the weather is doing over a particular location, right? But it's basically the column deep picture of what's going on. So I actually took the sounding from Maniwaki this morning, right? So this is the latest. You can see the timestamp on the bottom here. This is 7 a.m. from this morning, right? So that's the last weather balloon that we launched this morning. And this is the temperature and moisture profile at Maniwaki. So for one thing, you can see that our winds are generally speaking from the west-northwest. So the winds are coming in from the same direction throughout most of the atmosphere. the temperature, this is the 0 line here. Oops. So temperature is below freezing just about at every level. Well, it is below freezing at every level. And at least at Maniwaki, as of this morning, it was not completely cloudy. Right? We basically had a region or a spread between the temperature and the dew point, but it has actually gotten progressively more cloudy as the day has progressed. Any questions on how to read this? There's a lot of lines on here on this particular map. I'm not worried that you know what those other lines are. I literally just want you to know the vertical and the horizontal lines, which are the temperatures versus the pressures, right? So the vertical lines are lines of constant temperature, and the horizontal lines are lines of constant pressure or height. All of the other sort of gray lines, et cetera, on this curved lines, et cetera, are lines that I don't need you to worry about, at least for the next month or so. Yeah. Okay, so like I would say that generally speaking, a good rule of thumb is that if the temperature and dew point are less than 2 degrees C apart, there's a decent likelihood of clouds. If they're more than that, then your odds of clouds start to diminish pretty rapidly. So actually the area that I circled here would suggest that there isn't clouds because the distance between the temperature and the dew point is more than 2 degrees. All right, but we can actually see that it's getting cloudy as the day progresses. And I actually believe the forecast is for snow to develop this evening and tonight. Not a lot, but there's supposed to be like 2 to 5 centimeters worth of snow that's going to fall tonight. Oh, yeah. So usually the balloon bursts long before the 12 hours is up. So the balloons are designed to rise to a certain point, but then eventually the pressure outside of the balloon becomes so low that the balloon bursts, and then the package actually has a little parachute attached to it, and it just falls back down to the ground. And they're really light, so, but yeah, then they just fall back down to the ground. Most of them end up out over the ocean by the time the balloons burst, right? I mean, there's a lot more ocean than there is land. But literally, the packages are about this big, and they each weigh something on the order of like 120 grams or something like that. Now, in terms of monitoring precipitation, the primary method that we have to do that is radar imagery. All right? So radars actually transmit microwave radiation. So radars emit microwave radiation, and then that microwave radiation reflects off of droplets of rain or particles of snow, and the part of the signal that comes back to the radar essentially lets us know how heavy the precipitation is or how intense it is. So the radar reflectivity, right? And so when we say reflectivity, we're literally talking about how much of the signal is actually being reflected back to the radar dish. If none of the signal is being reflected back to the radar dish, that means that there are no particles in the way and the beam is just going out into space. So the primary portion of the radar is essentially the antenna and the receiving dish, right? And so that sends out a pulse. And one thing that you'll notice is that the pulse is actually angled slightly with respect to the ground. All right, so it's actually angled slightly upwards. So the further you get away from the radar, the higher in the atmosphere you're actually looking. Okay, so it can be a little bit deceiving. If you're very far away from the radar, you can be seeing precipitation, but that precipitation may not even be reaching the ground, right? It may be evaporating before it reaches the ground. If you're really close to the radar, then that precipitation is pretty close to the ground as it is. So we can actually tune the sensitivity of these radars. And when we know that there isn't any precipitation in the area, we can actually increase the sensitivity. And so we have something that's called clear air mode versus precipitation mode. And basically this is just how fine the sensitivity of the radar that we're looking at is. And so why would we even bother with clear air mode? Well, we can actually track wind movements by following things like insect plumes or bird plumes. So we can actually see sort of flocks or swarms of insects or birds, et cetera, on the radars when we're in clear air mode. And then we can relate. And so these are empirical relationships where we can relate how much signal is sent back to the radar to how much rainfall is falling. Okay, so when we're in the greens down here, we're essentially talking about precipitation amounts on the order of, say, a couple of millimeters per hour. But by the time we get up into the reds here, we're basically talking about things on the order of like 80 to 100 millimeters per hour. All right, so we're talking about very different rates of intensity. And the other thing to remember is that rain is actually more reflective than snow. So it's actually harder to see snow from a radar than it is to see rain. These are the NEXRAD locations across the United States. Now, it's kind of interesting. You'll notice that almost all of these correspond to airports. All right, so obviously we need to have a radar at every airport. And the main reason that these radars were actually developed was to prevent plane crashes. Yeah. Yeah, so you can't actually tell. So the question was, how do you know if it's snow or rain? So you won't actually know directly from just looking at the radar image. You have to have other information that's telling you if it's rain or snow, right? But that'll change the intensity that you're seeing. You can adjust for it. So what happens is in Canada, right now the radars are default set to snow mode for this time of year. Okay, so in a situation where we're actually getting rain, it'll look like the rain is heavier than it actually is because the radar is already been tuned to capture snow. So they've already increased the sensitivity of the radar. But there's no way, particularly of telling simply by looking at the radar image, whether you're looking at rain or snow. So these are the coverage of the radars, and then the circles basically are the range of each radar. And so you can see that at least for the United States, there is very little of the country that isn't covered by radar. The gaps are few and far between, and they're mostly in the intermountain regions in the Rockies, but certainly along everywhere from, say, the Midwest towards the East Coast, we can see precipitation everywhere, right? So there's no place where it would be precipitating that we wouldn't be able to observe it with one of our radars. This is the radar network in Canada. And so obviously, because we have 1/10 the population of the United States and an area that is actually larger than the United States, our coverage isn't anywhere near as good in Canada as it is in the United States. We basically have southern Canada covered, more or less, right? But anything north of sort of the population belt, and again, so we have no surface observations. We have very few surface observations up there. We have very little radar data up there, little to no radar data up there. So you can imagine if you're flying into an airport, you know, one of these small regional airports, the odds that you actually have a really good idea of what the weather is actually doing at that airport is not that great. All right, which is why it takes a certain breed of people to fly like the small planes up there, because it is an inherently more risky proposition than flying across the sort of southern tier, right, where we have this full observation network to tell us what's going on. And McGill has its own radar. So McGill has its own radar site, and you can access it. Hopefully it is up. Yeah, okay, so this is the McGill Radar Observatory. And you can get a reflectivity animation. And there's nothing to see right now because there's no precipitation in the area. But you can actually check this later tonight to actually see when the snow is moving in, right? And so McGill is situated right about here, right? And so you should be able to watch the radar reflectivity come in, and you'll be able to tell when the snow should start by actually tracking where the radar reflectivity and how fast that is moving into the area. There's also a US network. And so you can click on any station So it turns out actually that the Burlington radar does a pretty good job of capturing what's going on in Montreal. So you can actually see some precipitation is actually starting to show up on the Burlington radar, right? And this is actually going to be moving northward as the day progresses. So we're just starting to see some precipitation starting to show up. So this is Burlington over here. There's Montreal. And so you can see that there's, it looks like there's some snow now, maybe around 3.5 hours south of here. At least by car. Not saying that it'll start snowing in 3.5 hours, but about 3.5 hours car ride from here, there's actually snow. And you can also see regional images that give you a summary. And we can actually play a loop here. Where's the, oh, here, go to loop of this image. And so you can see the reflectivity, the precip sort of moving from southwest to northeast over time. Okay, and so that's an indication that we will be getting some snow a little bit later tonight. Yeah. What's that? Yeah, so generally speaking, when you see images like this, anytime there's large reflectivities, all of the radars will be in precipitation mode. Like generally you won't, like when we're in clear air mode, you generally won't see anything. Yeah, so we're all in precipitation mode. The radars in the United States will actually still be set to rain in general, even for this time of year, whereas the radars in Canada will be set for snow. So the radars in Canada will be tuned to a slightly higher sensitivity this time of year in general than the American radars will be. One of these days, somebody is actually going to combine the data from Canada and the United States and make it easy for everyone, but that hasn't happened yet. Now, one of the cool things about Doppler radars is that it allows us to not only see the precipitation, but it allows us to see wind. Okay? So on the top image, what you actually see is an image of reflectivity. Oops. So this image up here, that's actually an image of rain. And where you see the red just means that there's really intense rain going on. And it turns out that in this case, what you're looking at is a thunderstorm. And you're not looking at any particular thunderstorm, but you are looking at a severe thunderstorm. Okay, but the really cool thing about these radars is that, we'll explain the Doppler effect in a minute. It actually allows us to see the wind. And so if you look at the bottom image is actually a depiction of the wind. And what you're actually seeing in this little area where you see the sort of cool colors and warm colors very close to each other, that's an area where the winds are actually blowing in different directions very close to each other. And what that is actually telling you is that there's a tornado there. Okay, so we're actually seeing, and so what we're actually seeing is the speed. We're not measuring the wind directly. we're actually measuring the speed of the raindrops. Okay, and we're inferring the wind speed by saying that, well, the speed of the wind and the speed of the raindrops are probably about the same. Okay? And so, how many people have heard of the Doppler effect in general? Okay, so the most common example I think that people tend to give when they talk about the Doppler effect is listening to a siren go by, right? So as the ambulance or fire truck or whatever is approaching you, the pitch of the siren seems to be higher, and then as it passes you, the pitch seems to go down. Okay, so why is that happening? Well, so let's say you have the siren, it's sending out this sound wave, right? And so the sound wave is reaching you, and the peak of it is reaching you, but as the ambulance approaches you, the distance between you and the ambulance decreases, so it takes progressively less and less time for each sound wave to reach your ear. All right, so it's basically like, imagine if I was standing here and I just threw a ball, but then I actually got closer to you and then threw the ball at the same speed. That ball would reach to you in less time than when I was back here. Right? So you're actually, so what's happening is because the sound waves are reaching you at a faster and faster speed, it seems to have a higher frequency, which makes it sound like it's a higher pitch. And then as the ambulance passes you, the opposite happens. The distance between you and the ambulance is continuously increasing, which means that each sound wave, each progressive sound wave takes a little bit longer and longer and longer to get to your ear. So the distance between the peaks actually seems to be a longer distance, and we perceive that as a lower pitch. And so the radar sees the same thing. So the radar sends out a signal. If the thing that it's reflecting off of, if the raindrop that it's reflecting off of is actually blowing towards the radar, then the frequency of the signal coming back is actually higher than the frequency of the signal that is sent out. Whereas if the raindrop is moving away from the radar, the frequency of the signal that's reaching the radar is actually longer or lower than the frequency that it originally left. So the radar, just like your ear, can tell whether the siren is moving towards you or away from you. The radar can also tell if the raindrop is moving towards the radar or away from the radar. But that's all it can tell. It can only tell if it's moving directly towards the radar or directly away from the radar. That's the only thing it can distinguish. And so we can actually tell which way the wind is blowing by kind of inferring what's going on from. Okay, so let's pretend, we're going to take some time to go over this because it can be a little bit of a tricky concept, but once you get it, it's actually pretty straightforward. So let's say that this is the radar at the center of our image there, right? So I circled the radar. And so what the radar is doing is it sends out a signal, it rotates slightly, it sends out another signal, rotates, and it sends out a signal, and it basically sweeps out 360 degrees, right? So it goes in a circle, okay? Because it's basically getting an image all the way around the radar. So everywhere it's sending out a signal, you know, and sending out beams away from the radar. And so there's going to be portions of the image where the raindrops are blowing towards the radar. There are going to be portions of the image where the raindrops are blowing away from the radar. And there are going to be portions of the image where the radar cannot actually detect any wind at all. Okay, and so what might that look like? Well, let's assume that in this case, the wind is blowing in the directions of the arrows, of the gray arrows here, okay? So when the radar sends out a beam in this direction, from that angle, the rain is actually blowing towards the radar, right? So it actually sees, that particular radar beam is going to see wind blowing towards the radar. When it sends out a beam in this direction, that raindrop is neither moving toward the radar or away from the radar. It's moving at right angles to the radar beam. So as far as the radar is concerned, that is zero wind, because it cannot actually detect that the wind is blowing. Now when we go to this radar beam, now the wind, those raindrops are actually moving away from the radar. And so what we end up with is an image that looks like this, where in the cool colors, everywhere where you see the cool colors, the radar thinks or sees the wind blowing towards the radar. Everywhere where you see the warm colors, the wind is blowing away from the radar. And where you see the grayish colors, it basically sees no wind. And basically that tells you that the wind is blowing like that. And the easiest way to tell the direction of the wind is to look for the zero wind line. And I'm going to show you that on a different image. Okay, so same idea. Here's our radar. Again, the cool colors are winds that are blowing towards the radar. Warm colors, winds that are blowing away from the radar. And the grayish is the zero line. Well, you just draw lines from your radar along the zero line. And then you know that the wind has to be perpendicular to those radar lines. And so that basically tells you that the wind is either blowing in this direction or in this direction. Now, you then use the colors to help you determine which of those two directions it is. So since the cool colors are on the bottom of the image and the warm colors are on the top of the image, we know that it has to be this line because the wind is blowing towards the radar down here and then away from the radar up here. So we can actually use this to interpret which way the winds are blowing. This generally isn't that important unless you're in a thunderstorm where the winds can change speed and direction over very short distances. And that's when this becomes important. In fact, like the top 5 aviation disasters in the United States previous to the 80s were all because of unresolved wind around thunderstorms near airports, which is why these radars were created. And that's the purpose, the raison d'etre of these radars. And so now we actually use them. We actually use radars not only to tell us when and where precip is happening, but we also use them to basically help tell us when there are tornadoes or not. And so this is just the same sort of idea. All right, so here's your zero line. You know that the wind has to be perpendicular to your zero line. And the fact that the cool colors are here and warm colors are there basically tells you the direction the wind is blowing. And so I'm not trying to get you to understand the finer points of this. I just want you to kind of be able to understand by looking at an image, roughly speaking, which way the wind is blowing. Now, when we talk about small-scale winds around a thunderstorm, so we can actually have a situation where the wind, if this is the radar and it sends out a radar beam, where along the beam itself, the wind seems to be changing direction. All right, so that actually, what that actually tells you is that there is a giant plume of air descending from the sky, hitting the ground and spreading out. And this is called a microburst. And this is one of the phenomena associated with thunderstorms. And this phenomena is actually the biggest killer of people in aviation prior to the advent of this radar. Now, if the wind changes direction, again, here's your radar. If the wind changes direction on either side of our beam, that's a tornado. If it changes along our radar beam, if it changes direction along our radar beam, that's a microburst. If it changes direction on either side of our beam, that's actually telling you that there's rotation going on and that you have a tornado. And I actually think I'm going to end it here. So I will actually, on your homework assignment, you will see examples of things like this to kind of give you a little bit of practice as to what's going on. All right.